Thank you all for joining the webinar today. We're going to talk about inspecting tubes and pipes with the GelSight technology. So just before we get started, a couple items here. I'm Abby Lindberg. I'm the Director of Applications Engineering. And we'll be recording this session and putting it on YouTube after this for reference. And we'll also have the chat going for Q&A. The Q&A functionality might be disabled, but go ahead and use the chat. We have Frank Chang from my team answering questions live, and we'll have some time for questions at the end as well. With us today, we have Mark Cejer, and I'll pass it over to him to introduce himself and kick it off.
Great, thanks, Abby. Hi, everyone. I'm Mark, and I'm the sales leader for GelSight in the Midwest part of the U.S. And I've got some quite a few customers actually involved with testing and inspecting various types of pipes and tubing and related kind of surfaces. And these can be found in the aerospace industry, looking at things like fuel lines or landing gear, ductwork, manifolds, various engine components, as well as other industries like the nuclear energy industry, where tubes and pipes are very commonplace, and there's quite a bit of maintenance and repair that goes on when they shut these sites down for their maintenance cycles. And then other industrial type of applications. And what all these industries have in common, and all these kinds of parts have in common, is that for one, they're round, and secondly, they're reflective, and in most cases, they're very complex geometries. And so when you put those three things together, it can make inspection very challenging. And so that's what Abby's going to take us through, are some of the more common inspection applications that we see, like weld analysis, scratches and dings and dents, roughness. So RA is a very common parameter that's measured, especially for pipe fittings. And then pitting and corrosion is another one. And in all these applications, a lot of the existing methods, whether it's using hand tools or traditional tactile methods, they can lead to test escapes. And by that, what I mean is customers could be passing parts that are really bad, or they could be failing parts that are really good. And in both cases, it can be very, very expensive to solve those problems. Or they're using legacy methods that just take too long to operate. So one very common one is to use replica putty to take a mold of that defect and then send that off to a lab for analysis on a lab tool. So that's a workflow that on a good day is going to take at least a half hour. And many customers complain about taking multiple days to actually get their results back. So Abby's going to show us how to use the GelSight system for a lot of these measurements, and hopefully it'll be applicable for some of your applications. And Abby, let's take a look.
Thanks, Mark. Let me just stop sharing here. And before we get into the live demonstration on the samples that I have, we'll start with a little bit about how GelSight works. With us today, we're going to be using, we have our Series 2 system, and I also have Modulus with the 16mm straight lens. And we're also going to be using our new 2090, the high resolution 90-degree access lens. And all of these work in fundamentally the same way. So we have a camera, a lens, and an illumination system. I'll turn the light off here so we don't have to look at that while I take the gel out of it. So we have the camera, the lens, and the illumination system. And when I click this button, I'm actually taking a series of images, 6 images here, one with each one of these banks of LEDs illuminated. And we use those 6 images with the 6 different lighting orientations to basically calculate slope based on pixel intensity. And that's what's giving us our 3D data. And then in conjunction with that, we're using a gel sensor. And this lets us look at surfaces regardless of optical properties. So, glass, metal, textile is all going to look the same to us because we look at everything through the other side of that gel. And, I mentioned all of these systems work in the same way. We're just talking about different form factors at this point. So we've got our smaller one with the modulus, and then we have smaller and higher resolution with the 2090 lens. So I'll just attach this, put this gel back into my Series 2 system here, and then I'll go ahead and share my screen. So I'm going to switch the video so we can see the desktop here as I take the scans, and I'll also share the GelSight mobile software. And if you want to make the GelSight mobile software larger, you can click on that, or the video screen share larger, you can click on that to kind of toggle between the two. So let me go ahead and switch the video here. All right. And we'll share the GelSight screen share as well. All right, so hopefully we should be seeing that now. And the first sample that we're gonna look at today is gonna be this Y-Connect piece. I'll kind of move the modulus out of the way for now. And Mark was mentioning weld inspection, especially for tubes and pipes, and this one has a big weld down the side of it. And we'll take a look at that, and we'll do some analysis first. So I'm going to take our Series 2 system with this, as we have the larger field of view, and for this larger weld, that'll be a good fit. And I'm just going to press this onto the surface and take the scan. Now our 3D data is being generated, and we'll open that up. And here we can see the reconstruction of that surface. All right. So I'll jump back over and we can start to talk about the analysis here. So we have a couple different ways we can analyze welds. I'm going to show the weld bead function on this specifically, but another option would be to use our offset function, which is basically a profile function, checking the profile along this weld in multiple locations. So we'll talk about that one later in another example. But for now, let's go ahead and open up our weld bead analysis. So I just selected weld bead, and we can see our output here. We're seeing the height of the weld, the width of the weld, and we're seeing the planar mismatch. So as these two pieces were welded together, is one side a little bit higher than the other side? That's what we're looking at there. And we also see an undercut depth. And in this case, we don't have an undercut, but if when this weld was created, if any material kind of dipped below on the sides of the weld, that's what we would be measuring there. And we also see these profiles at the bottom here. And this is actually what's giving us that planar mismatch result here. And we're basically leveling the surface from the left side and leveling the surface from the right side. That's what you're seeing on the bottom here. Blue would be leveling it on the left and red on the right. And then we're looking at the difference in height, depending on which side we level it from. And then, of course, we can turn this into our PDF report as well to attach that to, whatever system you need to include this analysis on. You can zoom in on these as well. Now for the next example, I'll pull something out a little bit different. I'll pull up we'll switch back over to capture here. And I'll take out our fuel line here. So we've got this one here. And there's a little defect in this elbow. And we can see if I try and access that with Series 2, I actually can't quite make contact with the surface. So in this case, I'm going to switch over to our modulus system with our 16mm lens. So I'll just unplug our Series 2 and we'll plug in our modulus. And I'll move this out of the way a little bit. All right, and now we've got our modulus with our straight lens live here, and I'll come in and measure that defect right at that elbow in here. So I'll go like this. There, that's a pretty good one. Come in there, and I'll just click the button to take the scan. And we'll go ahead and open that scan up in just a second here. And we'll take a look at the 3D again here. So you can see what that curvature looks like at that elbow there. Now for this, you might be interested in the depth of that defect, right? So I'll go ahead and I'll use our defect detection function on this. And we'll just draw a box kind of around that defect and click Analyze. And the output that defect detection gives us is all of the characteristics of that defect, in addition to the profile through the deepest point. So we can see our length, width, area, volume, and depth. And we can see this color map, and the profile is automatically drawn through the deepest point. So that's what we're seeing right here. And we're measuring from that deepest point to the average of our reference surface. Now, something else we know is interesting in a lot of these applications, it might be the radius at the bottom of a defect. And maybe the radius here is fine, but maybe the radius over here looks like it's a little bit smaller of a defect in the XY direction. So maybe we care about that smaller radius here. And we could include our radius measurement at the bottom of that defect. And to do that, I'll just add our profile geometry function. And we'll just draw a profile across our defect here. And we see this kind of sharp looking edge here. And where we have these smaller radii, that's really where you're more likely to form a crack as opposed to just being a scratch. So this is often something that our customers care about measuring. So for this, I'll just come in and we'll adjust our measurement region just to fit that space there. I'm going to zoom in on that, and you can see that fit along that profile. And then we can see the radius being reported there, almost tooth out, really. And then, of course, we can turn this into our PDF report again. So I'll click PDF to generate that. And since we have multiple analyses performed on this, we'll actually have 2 pages of our report. So we can see, our radius measurement here, and we can see our defect detection analysis here. And next, I'll actually switch back to the first sample because I want to show another example of an application at an elbow or a bend in a pipe. And this one also requires modulus to access it. So I'll actually pull this out again, and we'll look at this area here. And we have some kind of, rippling in the metal here from that bend. And this is something that we have a bunch of our customers want to quantify as well. So I'll actually just take a scan of that. We'll take a look right here. You can see those kind of vertical lines in the field of view there. And we'll click the button to take that scan. All right, we'll open that up. And we can really see those features there. And let's go look at the 3D again on this one as well. And we have a couple other controls from the 3D display. So in addition to just moving it around and looking at it from other angles, we can increase the scaling, maybe see some of those smaller features better. And we also have an option to change the lighting orientation. So maybe you can see those basically rippling a little bit better if you change where the light is coming from on your 3D display. So just some optional customizability for the display to really let you see what's going on your surface. So we'll reset that and we'll come back over to this view here. And I mentioned our offset function doing multiple profiles for weld analysis, but we could also use our offset function for something like this. So I'll come in for offset. And basically, we're just looking at a profile across this surface. So we can see the profile down here, and you can see the curvature to it. What I'm going to do next is just remove the form of that surface. So I'll add a reference surface here. And then we'll tell it it's second order to remove that curvature. And now we can see that profile here. And maybe I want to measure multiple profiles and average them or find the minimum and maximum on this as well. So I could come in here and say, maybe I want 9 profiles evenly spaced within this width here. And we'll click Analyze. And now we can see how all of those profiles sort of stack up across that area here. And we could come in and measure it. Maybe we need to know the minimum value here to the maximum here to get that difference in height from, right before this ridge and right after it. And we can see that's about what the average is about 4/10. So talking pretty small right now. All right, so I'll go back over to capture and we'll take a look at another surface on this. So I have with the Y-Connect that we have here, we often care about sealing surfaces on tubes and pipes. So we have this kind of lip in here, which would be a sealing surface. And we're going to go ahead and measure the surface finish there. And this is going to require us to use our high resolution modulus attachment because we need the accessibility from modulus. And we also need the high resolution because these surface finishes are typically on the low end. So I'll just go ahead and switch out our lens attachment here. We'll take our 16 off. And we'll put our 2090 on for our high resolution option here. All right. We'll head back into capture now, and let's see if I can find where we're going to measure on here. So we've got right inside this edge here is what we'll take a look at. So I'll press this down. We'll go like right here. And we'll take that scan. And that is just right inside the edge like that. All right. So we'll open the scan up and we can see that texture along that edge here that we care about. And we have a couple different ways that we can measure roughness for this. So I'm going to start with profile roughness, and that's going to give us a bunch of R parameters, and one that comes up really often is RA. That's what we see typically on a lot of specs, a lot of pieces of paper that tell you what you're going to measure. It's typically RA. And then we'll talk about some other parameters as well. But I'll come in here for profile roughness, and we'll draw a profile perpendicular to the lay of that surface texture here. And now with this, we can also do multiple profiles. Maybe I want 5 profiles. And we'll average them. So this is effectively like taking 5 trace lengths with your stylus, but just at one point, as opposed to having to do 5 separate scans or 5 separate measurements. And we can see at the top of our results here, we've got our average RA, so the average of all 5 of those profiles. Now we can also take this and measure surface roughness instead. So profile roughness is giving us roughness along a line, whereas surface roughness will give us roughness over an area. So I'll click surface roughness and we can compare that as well. Maybe I'll use this to draw a shape here. Something like that. And we'll click analyze. And that polygon tool for drawing really lets us do, customize these shapes. Maybe it's not a simple rectangle or flat surface that we're looking at, and we have to get a little creative with how we draw that region. And if I scroll up on the top here, we can see our S parameter outputs. So we can see SA is basically your RA equivalent, but over area as opposed to along a line. So you can see our SA, or average roughness, is about 36. It's pretty close to what we got just along the profile, actually. And we also have these other S parameters. And there are a lot of these are pretty relevant for sealing surfaces, especially something like SDQ. I'll kind of mouse over that so you can see what that looks like. But that's your RMS value. And this is going to give you, basically some information about the slopes of the surface within your region here. And that can be particularly interesting for sealing surface applications. And now we've got one more example. So right in kind of a similar area inside of this sample, just a little bit further in, we've got some pitting and corrosion that we'll take a look at. All right, I think we've got it right here. So I'm going to take our 20 as well for this application, our 2090, and we'll come right in here and we can see that pitting on the surface there. And this actually looks like, it was some pitting that was then smoothed out to remove it, to keep this in production. Obviously not anymore. I'll go ahead and open that scan up, but this might be representative of, you saw corrosion, you repaired this part, and you want to see if it's able to go back into production. And for this, we'll go ahead and use our pit detection function. And this will run on the whole field of view, or you can draw a region of interest, and it just picks up all of those pits that are left behind after our smoothing or repair process. And we can customize, we can add filters to this. Maybe we don't care about them until they're a certain depth, so we know there's passing or failing pits involved in this. And we can also sort our table or select something from our list and highlight it there. And this is all exportable as a CSV file as well. And the last thing that I'll mention, actually from the Explore page here, I've taken a few scans of these samples in advance, but we can see all these scans that I've done analysis on, and maybe, a few of these are the same part. These last three were all the same sample part. Actually, these four of them were. And I could actually export all of that data to Excel or create a merged PDF report with all the data from all four of those scans in one report, instead of having individual PDF reports as well. So that can be a really nice feature to tie all of your data in together for each part that you're inspecting. So with that, I think I'll stop sharing, and I'll hand it back over to Mark to summarize what we just talked about and the kind of the value that GelSight can bring to these types of applications.
Yeah, great. Thanks, Abby. Nice job. Certainly what kind of jumps out for me in these, and I hear this a lot from our customers, is that portability, right? We're taking the lab grade performance and bringing it out to wherever it's needed on the shop floor, out in the field. The various probes that we have give access to a lot of places on parts that just other technologies, it's troublesome, right? It's just very hard to get access to. And of course, the speed of the measurements, Abby's getting results in under a minute for each of these measurements that she's taking. And we continually get feedback that the user interface is quite simple. It's got a very quick learning curve, and it's easy to operate for just about anybody. But the thing that didn't jump out is the accuracies and the repeatabilities that we're talking about here, or that Abby was demonstrating. These systems that she was showing have sub-thou level accuracies, or micron level, and in many cases sub-micron level accuracies as well. And these are fully 17025 traceable accuracies. The roughness capability of that modulus probe that she demonstrated will go down to a RA of 8 microinches, or 0.2 microns. So these systems really have some capability that's just unmatched when you put it all together in applications like what we're just showing here for very common parts that are throughout various industries. So thanks for Abby, thanks for the good demonstrations on that and showing us how the GelSight system operates.
Thanks, Mark. So I think with that, we have some time for questions. So I'll give everyone a couple minutes to add some questions to the chat here. I don't see any in there yet, so let everyone have a couple minutes. Maybe light on the questions today, Mark. So
Yeah.
Okay, we've got a couple coming in now. So when is the next demo? We're happy to reach out to schedule a demonstration to you and your company or organization. Otherwise, we are doing webinars monthly, so we'll definitely be sending out a July one at some point. Mark, feel free to add to that.
That covers it well. Thanks.
All right, in the pit assessment function, what is the maximum pit depth? So there's a couple of factors when we're talking about the maximum depth here, and some of it's going to be related to the aspect ratio. So depending on the system that I have, we're looking at about 1 millimeter for the maximum depth that we can measure for, for Series 2 and for modulus with the 16 millimeter here. But that does depend on the aspect ratio. So you can imagine if we had a really narrow crack that was very deep, the gel might physically not get to the bottom of it. So that can be a big factor when we're talking about the maximum depth. It ends up being a little bit of it depends, but we do test and qualify up to 1 millimeter reference standards. All right, factoring in the radius of small diameter tubing, how do you measure a gouge from what was the peak of the tube? Okay, so I'm assuming, and I could be wrong, but I'm making the assumption that we're talking about if there was a gouge kind of on this edge here. And I did use our defect detection function, and that does automatically fit a second order form to it. So we can handle curved surfaces or flat surfaces with that. We can also use our offset function that I showed on kind of the elbow of that larger diameter, and we can basically manually tell it that we're looking at a curved surface as well. So it depends on what analysis function we're using, but we can have some of them where we manually tell it what the reference surface is, and some of them where that's an automated process.
Yeah, and then the scratch tool can also get used to measure the height of any kind of displaced material from a gouge. So sometimes you want the deepest point and then also the highest point of raised material. And the system has that capability as well.
Yeah, great point. Measuring peaks. We didn't do any of that today. We just did negative features, but we do have tools for positive features as well. Can the system be set up for real-time reject or pass? Yes, we can add pass-fail criteria to any of the outputs that we talked about today. Anything that showed up on that right-hand side, you could have pass-fail criteria for that. All right, we do have a question here about using GelSight on a custom submersible with waterproofing. So I think we might have to follow up with you after that on this one. I don't know if anybody's doing that yet, but we can talk. Mark, I don't know if you have any other information about that.
No, I don't. That's worth having a conversation for sure.
Mm-hmm. How is this calibrated to see the measurement are correct to NIST measurement? So we didn't get into the calibration details today, but we do calibrate each gel before we can use it. And I do have I have the calibration standard for modulus here. And we can see, I'll slide it to this one. I've got this groove target here, and the depth of that groove and the distance between those two holes are certified dimensions. So we use the third-party lab, East Coast Metrology, to certify these reference specimens. And they're going to give us that X, Y, and Z traceability on this groove target as part of our calibration process for each gel. All right. Following up on George's point about custom robots, is there an SDK that comes with the device to allow integration? Yeah, we have an API, and it's available with our Pro software. It's available on GitHub, and we have some customers that are already doing their custom integration. Whether that's integration onto a robot or integration just to automatically transfer data to an MRP system, both of those are options with the available API. And we've got Ethan saying they have 3 units and they're amazing, so thank you. All right, and we're pretty much just at time, but I've got a couple other questions here, which we'll stay for. How does the lateral resolution compare between modulus and other models? So when modulus was designed here, the 16 millimeter one is designed to pretty much be comparable to Series 2, and the 20 is designed to be pretty much comparable to the Max system. And then we have the last question here. This is, when will this video be uploaded to YouTube? And that is pretty much as soon as I get to download it and then send it out. So it should be today. All right, so thank you all for joining. And thank you, Mark, for joining too.
Great. Thanks, Abby. Thanks, everyone, for joining.
All right, thanks.
Bye.